Okay, so yes, so if you speak, you will be recorded in infamy right now. So this, Mr. Bells, this is GOA test review for transformations. So what we're going to try and do right now is make sure that we know everything that we can about these things called transformations. And we'll start off with some basic stuff, and that's rigid motion ones. So rigid motion ones means that they're going to be the same size and shape after the transformation. Or in other words, what's our big C word for that? Congruent. Oh, look at that. That actual thing. So that they're going to be congruent. We know that there are 4 specific ones that we've studied in this unit that gives us rigid motion transformations, and their translations and their rotations. And I'm going to kind of put those together like this because they preserve. Preserve means it keeps it the same. Preserve orientation. And that's kind of an important thing to be able to know, to separate if you're not sure what something's doing or not. So they preserve orientation. And then reflections and glide reflections. Now this textbook doesn't separate these as much as what I have done in class, but know that they are. And these close to preserve, it's almost using the exact same letters, but they reverse orientation. And it's kind of an easy way for you to be able to tell what the heck's going on. Okay? So quick little pictures. Translations simply means that a shape can slide in any direction, up, down, left, right, or on a diagonal, and it won't lose its size and shape. And we know that these things are, this translation thing has something called a, what's our V word? That was me asking the class in here, what's the V word for that translation? Oh my gosh, you guys didn't hear it, but they all screamed out vector. That's a vector, because a vector has a magnitude, right? A magnitude and amount. Magnitude. In this case, in our class, we did distances every time, a magnitude and a direction, which means it'll go so far in a certain direction. So those are translations. And then we had this one. We had a flag here, and then we had a flag here. And this, you can see a lot of people sometimes want to put a reflection, like there's a line there, but nope, you can see the flag. If I go up the flagpole and around the flag, that is a clockwise movement. And if I go up the flagpole and around the flag, that one's also clockwise. So that means these two things have the same orientation. So we know if they preserve orientation, they have to be either a translation or rotation. And this is obvious that I can't slide that one directly on top of that one. So this is a rotation. We have a couple of key things with rotations. We want to know how far it rotates. This one definitely looks like it's approximately 90 degrees. I'd have to put a right angle in there to know for sure that it's 90 degrees. And also, we have this dot right here, which is called the center of rotation, which simply means that that's where it's spinning around. Now, the center of rotation doesn't have to be on the object itself. It could be any place that we want to put it. We just simply know that if the shape is here now and the other shape is further away like this, that center of rotation would have to be someplace in this general vicinity over here. Okay? So, I think we're good on that. So that's rotation. So reflections. If I have a flag like this, there's some line someplace that I could flip this over and it would end up just over here. Maybe I should have done this too. So this would be my original one. Call that flag prime, call this flag prime, call this flag prime. So we know that the one that doesn't have the little dash on it is the original one, or what we call a pre-image. Pre-image. And the one after is called the image. Okay? And the reflection could be on a vertical line. The reflection could be on a horizontal line. Look like that. Or it could be on a diagonal line. So I could have something that looks like this, and then another one that looks like this, where that kind of goes like that. So our ability to be able to perform a reflection using something like this could be beneficial. You can see that I can put it right on that line, and if I look through it, it should show up identical on the other side of it, or pretty close. I freehanded all these, so they're not going to be perfect. But we also know that anytime that I take these points and take the original point, there's my flag prime, take the original point and its image, so like this is A and this is A prime, that this line of reflection is also a perpendicular bisector of A prime of that segment. That has to be true every time in order for it to work. So everybody go to that? Yep, I know I've said a lot of stuff in a row right now, but I'm hoping this is just kind of review-ish things. So now I've done translations, and I've done rotations, and I've done reflections. Just kind of getting a basic thing. And all of these, again, are rigid motion transformations. And my last one is, of course, a glide reflection. And that's a composition of two of them. So it would look just like this. Assuming these were all the same size. Kind of looking like footsteps going on. So to get from here to prime, or to get from prime to double prime like this, I'd have to do a reflection followed by a translation to get it from here to here. Okay? And you know that both of these ones, reflections and glide reflections, we said reverse orientation. And I'll kind of go through that right now just to make sure that we're clear on it, what that means. So right up here, here's my pre-image. So I'm going to go up the flag and around the pole, or up the pole and around the flag. So this is up and around, and you can see that that is counterclockwise. Up and around counterclockwise. This one, up the flagpole and around the flag, is clockwise, and those are definitely opposite, right? Clockwise and counterclockwise. So those do reverse orientation, whereas these ones preserve orientation. So that's your basic stuff. First, for transformations in rigid motion. Then let me go ahead and talk about this. Just had a panic attack there for a second. I wasn't sure that I started recording the video, and I'm like, man, that would stink. But we still got everybody with us. So the other one that we really talked about in this class just recently was a dilation. And a dilation has some sort of size change. So we would take a flag that looks like this and maybe blow it up like that. So that's a dilation. So this is not rigid motion. This is not rigid motion. It has, it's not that, because they are not congruent from the beginning to the end. Good deal? But if I was to take these things and connect from key point to key point at some place over here in the distance, those lines would intersect, and that is the origination point for the dilation. So origination. And based on these distances here, we can tell exactly what's going on with this. So if it was right over here, and I was to say that this distance right here was 2, and this distance right here was 4, then I would know that I could take the total distance of the long one, assuming this is my secondary one, 6 over my 4, 6 being the whole length right here, 4 plus 2, 6 over 4, what it was to my original shape, and I would know that that's a 1.5 in this case. Okay? So you can take a look at dilations that way. We could also look at it just from the size of the shapes in terms of if this distance was x, whatever number right there would be in front of x, in this case would be 1.5x. And we talked two different ways with this. We said that if that scale change is that per length, then we'd know it'd be that scale change, size change squared for area, and that size change cubed for volume if we were to do volumes, which we didn't really do in this case. One of the classes, I think we talked about it. I don't know if it was this one or not. Okay, so those are dilations. Those are not rigid motions because they're not congruent, but they are one of our transformations. Good deal? And they can get bigger if it's greater than 1, and they can get smaller if it's less than 1. Good. And most of you are just kind of nodding along going, yep, I knew all this stuff. This is just making me feel even better about tomorrow, knowing that I'm going to be a rock star on this, yeah? Okay, so what would happen if I actually ask you to do some of these things? Well, we know that we have an entire sheet of transformations, right? So that xy could become something like this, x plus 3 comma y minus 5. And you should know just by looking at this notation transformation exactly what that's going to be. So give me a quick thumb up, thumb down. How many of you know exactly what type of transformation this is, what it would do, where it would go, how does it work? So for the people that are home right now, I don't have them videotaping here, but I don't see any thumbs up. I have a side, oh, I have one up, one sideways, 2 up, 3 up, okay, sideways. Okay, so this, I'm hoping all of you in here said, yeah, Mr. Bells, that is 100% a translation, and it should go 3 to the right, and, oop, I lost a T, and 5 down, 3 to the right and 5 down. So it takes any original xy coordinate and it's going to move it 3 to the right because it's x plus 3 and 5 down because it's y minus 5. And now people are kind of going, yep, 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 makes sense. Is that good? Sweet. So what about this one? X comma y becomes negative x comma negative y. Like that one, man, that's another one of those transformations. The question is this a translation? Is it not a translation? For those of you at home, hopefully you're just like, bam, I know what that one is. That is a big R of 180 degrees. That is a rotation of 180 degrees because it flipped it over the y-axis and flipped it over the x-axis. Changed the x, changed the y. Good. And yes, that entire big list that we have, you can see I have, I don't know, about 50 pieces of paper someplace over here is that list of all of those things. You can use that list the same way you can use all your theorems, postulates, properties, and definitions to know all of them. And that might be a nice thing to have. Cool. So let me give you one more in here. Let's go x comma y becomes, let's go 4x comma 4y. And count of 3, yell it out. 1, what transformation's going on? 2, 3. That's pretty good. That was over half the class that actually talked right then. So that is a dilation, and we know that it gets bigger or smaller. Bigger. Everybody agree? Bigger. Awesome. How much bigger is its area? How much bigger is the area of the shape going to be? 3, 2, 1. 16. 16 times bigger. Because we know that it's going to be 4 times for the length and 4 times for the width, or 4 squared, which equals 16 times bigger. Okay? So if I put this right up here on my piece of paper, I did this one right here, yes, and I did this one right here. Yes or no, that right there is an example of this specifically. Yes or no. 3, 2, 1. Answer. Silence. It's quiet. This should be a big ol' honkin' no. No, 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 no. Because this one shows that it should be a scale factor of 4. You can see that this one, from the picture already, this is pretty easy. It has a height of 3 right here, right? So that means that our new one should have a height of 12. And if I check it, I got 1, 2, 3, 4, 5, 6, 7. And it needs to have a height of 12 if it was this one. Okay? So what would this one's scale factor be? I would simply take that height 7, that height 3, and I would know it would be a 7/3, or equivalent of 2.3 repeating. Is that okay, everybody? Making sure we can check from the pictures as well as from the notations. Okay, so what else we got in here? We had this little section, and I know that we didn't cover it much in class, but let's see what we got here. Let's say we got a shape that looks like this, and I said, hey, does this have any symmetry? And your answer would be, it's supposed to. It's supposed to look like it does. The ones on the test will be even. Does it, yes, have a reflectional vertical line of symmetry? Yeah, everybody agreed? Does it have a horizontal line of symmetry? Yeah. And if it has 2 lines of symmetry that intersect, then we know that it also must have rotational symmetry. And when we talk about rotational symmetry, we refer to it in terms of how many degrees it takes to rotate directly on top of itself So this one would have rotational symmetry of 180 degrees. Because I could take this point right here, A, and swing it all the way around to here, C. We'll make this B, this one D. That A could rotate all the way to C, but it'd have to rotate 180 degrees for all the points to lie on top of all the other points. Is that good? Whereas if we had this shape right here, and this was a regular pentagon, that this one does also have rotational symmetry, yes? But it has rotational symmetry of 72 degrees. And some of you are like, where the bleep did you just get that number from, right? Because you're looking at this going, okay, I could rotate it once, twice, 3 times, 4 times, 5 times, and 360 divided by 5 is 72 degrees. That was from homework questions, yes? Or I'm not seeing the eyes that say that you are with me on that. Is that what completely foreign, or are we okay? Okay. So there's that kind of stuff. So I'm going to ask you to either put in symmetry lines or talk about rotational symmetry in a section on it. Okay? There's a section again, like what we just did, where I'm going to ask you to perform some of these ones. And there's another section where I have them already done, and you just tell me which one you think it is. Okay? So like if I had this, yes, and then you had this, I would say, hey, what is this? You would be able to tell me that this is a good deal. I'm hoping just a regular reflection, right? Because they're at the same heights. They're at the same heights going straight across. But is it over the y-axis, or is it over a different line? Did they flip over this line right here, yes or no? Nope. They flipped over a line right over in this area. How do I determine exactly where that is? I can count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes, yes? So if it's 9 boxes between them, where does the reflection line have to be? At the 4.5 mark? So I go from here, 1, 2, 3, 4.5. And you can see that this is a reflection over the line x equals 1.5. Lowercase r, reflection over the line x equals 1.5. That's what that one would be. And you guys, I know you did that in your homework online too. Okay? So there's that kind of stuff. We got these things. Right, we had mirrors where we did a line and we did another line, and we said, hey, what happens when I reflect this flag over parallel lines? So we're going to try it again. Class, I know there's only 6 of you in here. The end result when I reflect a flag over parallel lines is a what?
Translation.
Translation. Awesome. And I also learned that as long as these lines are parallel, that end result translation, if I reflect over A, then reflect over B, is going to translate whatever this distance is. So if this is 4 inches, it's going to end up translating how far? 8 inches, right? It's always going to go twice as far as what it is between the parallel lines. Now I could check this. I'm going to go ahead and put the mirror down. I'm going to look through this here. I'm going to copy my little shape. There's my flag. Then I'm going to reflect the flag over here. I'm going to do this one in green. That you can see that when I reflected this one to here, we're going to call this one prime. And then reflected this one to here, we're going to call this one double prime. That the net result from green to green is a translation, and that distance is double the distance between the parallel lines. But that's a fact. And that we know that if we were to do it over intersecting lines, and I reflected something over intersecting lines like this, that the net result is a rotation. And if this is 80 degrees right here, 80 degrees between the intersecting lines, that the rotation is actually going to be 160 degrees. So it's going to rotate twice as much as whatever the acute angle is. Is that okay? Now granted, if this is 80 degrees, it's going to rotate 160, or if this is 80, we know this is 100, it could actually rotate backwards 200 degrees, or double the obtuse angle in the opposite direction. So whichever way you want to think of that one. Good deal? And then we, in both classes, played around a lot with compositions. Which meant multiple transformations going on, right? So that if I went here, and then I went here, that this one actually is two things, or three things maybe. It could be a reflection, followed by a translation, and then, because I think this one's a little bit bigger than this one, yes? A dilation. So looking at multiple transformations at one time. And I'm feeling like we've covered almost everything. Yep, that's pretty good. So there might be some things like this where I go, hey, what is that? What type of transformation is this specifically? 3, 2, 1. Good. So we got to be very careful with this. This should be 100% just a reflection over that line. Is that okay? So be careful when we say rotations, because remember, if it's a rotation, then the orientation of the flag has to be the same from the first one to the second one. And this one definitely, this goes clockwise, and this one goes counterclockwise. It's okay? Last thing that you guys need to be able to do is be comfortable with this thing right here. So I'm going to call it good right now in terms of the review. It's 5 pages. Make sure that you know all this stuff, and that you practice this stuff, and that you have good things in your notes to be able to use. And we are